Hi, I'm going to talk about vibrations of polyatomic, polyatomic, just big molecules, and how you relate that to spectra. So I'm going to start with some spectra. Screen share, screen share. So here we've got spectra for, this is IR, very different than Raman. We'll get to what Raman is in a little bit. So we've got H, hopefully you can see that. So we've got H2O, carbon dioxide, and ethanol. So water, OH bending, OH stretching. CO2, you've got the bending is over here, and then you've got the stretching. There's actually two stretching modes. So you have the broader peak, and then ethanol. Ooh, crazy. Lots and lots of bands. Okay, how on earth do we know all of these different spectral transitions? So part of being a vibrational spectroscopist is doing what are called band assignments. And so you do a lot of work to identify that this is the OH bending. Well, what do I mean by bending? Well, let me see. If I do, ta-da! Okay, this is a Wikipedia page for molecular vibration. And it's got some great animations. So there are so many different ways that molecules can vibrate. It's not just about a bond molecule, two molecules vibrating like so. This is what the harmonic oscillator has been showing us. But when you have multiple atoms bonded together and they're all vibrating simultaneously in all these different directions, you need to classify the different types of vibrations. So if a particular molecule has multiple vibrations, each one is called a mode. And so you have the symmetric mode, the asymmetric mode, you could have a bending, you could have twisting, wagging, rocking. So in my PhD work, I was doing vibrational spectroscopy of polymers, and we were looking at a whole bunch of systematic rocking and wagging along the polymer backbone, so along the carbon chain. So you get to be really good at identifying certain types of molecular vibrations based off the spectra when you look at the spectra, like so. Okay, so let's focus in on water. I'm going to jump to the board and I'm going to explain how we know that this is the stretching and this is the bending. Stop share. Okay, this is what I love spectroscopy because I think this is so much fun. First of all, we know that there are 3 vibrational modes for water. How do we know that? So H2O, 3 vibrational modes. Okay, so first off, the number of modes is essentially the degree of freedom for vibration. Okay, so if you think about the total degrees of freedom, how many different ways can the molecules move? They can move translationally, this way, or this way. So there are 3 translational modes. Plus, when it's rotating, it can go this way, or that way. So 3 rotational modes. Then there's going to be the number of vibrational modes. Team, when you add all of those together, you get total degrees of freedom. Cool? Don't know that. We know this is equal to 3n, which is 3 times the number of atoms. Sweet. Side note, this is 3 rotational modes for nonlinear. If it's linear, this becomes 2 because there's going to be this one and then this one. You don't look at this one. If the molecule rotating like this, that's not enough of a change of its dipole moment such that you can have any translation or any rotational changes of its transition dipole moment operator. Therefore, we don't consider that a rotation. So if it's a linear molecule, it only goes this way or this way. It doesn't go this way. So X or Y, not Z. But vibrational modes, so you would say, okay, so 3n minus 3 minus 3 equals number vibration. Cool? Or 3n minus 6. So for water, we have 3 times 1, 2, 3 minus 6 equals 3 vibrational modes. Cool. Awesome. And looking at the spectra, 3 ones pick up. So you've got, oh, you can't even see that. Anyway, so you have something that looks like this. So you've got the 2 OH stretching and then the scissoring or the bending. Okay, go team. Number of vibrational modes. Cool. Okay, so let me talk about the bending stuff or the different types of modes. Okay, so now we've got, so 3 different modes, and I'll write in this as we go. So here's the symmetric stretching. So this is where you've got oxygen, hydrogen, and they're both going out like that. Okay, so that has a fundamental frequency of 3652. When you go through all of the rigmarole in your HCl, DCl problem, you will find what the fundamental frequency is. That's what was done for this. So if you think about the separations, the frequencies separating from the V equals 0 to V equals 1, V equals 1 to V equals 2, those are both going to be 3652 approximately. And so there's that spacing is going to between all the different stretching modes or stretching transitions for symmetric stretching is going to be about 3652. The asymmetric stretching is going to be a slightly higher frequency. And this one equals, what are you? 3756. And so that spacing is going to be slightly, if this is V equals 0, V equals 1, it's going to be slightly larger than this spacing. Okay. And then likewise the bending, whoops, let's do it this way. That angle is going to get smaller, and this is the bending. With polyatomics, they normally call it scissoring. But this is kind of a weird polyatomic because there's only one central point. There's no backbone. But then you've got, where are you? 1595. Question. This is a great exam question I gave a couple years back. Why is that one smaller? You got 1595, smaller frequency than the asymmetric and the symmetric stretching modes. So why would this one have a frequency that's lower than these two? Give you a second to think about that. Go team. So, well, think about the quantity of mass that's moving in terms of what you define as a vibration. And so, oh, the other thing is, so V equals 0, V equals 1, the transitions here, so the difference in these energy states is going to, that should be the same value, it's going to be about 1595. So these are much closer together than the transitions from symmetric or asymmetric. Okay, the other thing that's nice about this is because these are separated out enough, these are symmetric modes of vibration. They have a G value, so they have, oh goodness, a total vibrational mode, or sorry, total vibrational energy, that's each one of these added together. So you've got delta G total is going to then be the, see how I have this written, B1, B plus 1/2, this isn't, so when you're looking at your total vibrational energy, you're going to add, of the molecule itself, you're going to add all of these together. Now, all of these are going to be going through different transitions depending on what incident photons are upon them. So just because you don't measure it doesn't mean it's not there. Okay, so these are all going to be wagging and vibrating at different frequencies, but then you're going to see the frequency change if there's absorption, okay? And that absorption is only going to occur if you've got incident photons such that you can have the V equals 0 to the V equals 1 transition. Okay, so the fundamental energy of these molecules will be not the delta G, but just the G term, okay? And each one of those, because they're separate enough in their frequencies, will yield different energies. And this is a result of the Born-Oppenheimer approximation, where you can separate out those different energies. Okay, so real cool thing about the vibrational modes is if you have, so okay, so now let's talk about IR. If you have a molecule that is IR active, that means its vibrational mode causes a change in dipole moment. Okay, so if you've got your water molecule, and there's your dipole moment, as if you have the symmetric stretching, you're going to have a change in dipole moment. Okay, so if it's symmetric stretching, that means these get longer, which means this separation increases so that this gets longer. Okay, if you have CO2 and you have your two dipoles, and you've got, so it gets longer. And so this would be for the symmetric stretching of CO2, you have no change in dipole. Okay, IR inactive, IR active. Okay, now, and when I say that, this mode is IR active. The other modes might not be IR active. It turns out they all three are, because you can see all three in the IR. But CO2 is interesting. CO2 has both IR active and IR inactive modes. Okay. So if you have a change in dipole moment, so if you change in dipole moment, it is IR active. If you don't have a change in dipole moment, IR inactive. But if you have a change, so let's see. Actually, let me, instead of going into that, let me pause for a second because that gets into Raman. Yeah, I'm going to pause this video. So that's vibrational modes of IR. And actually, let me go back to CO2 and ethanol real quick, just so you can see it. And then I'll do a different video on Raman. But I want you to think about, back to the question of number of vibrational modes. So CO2 has, so 3 molecules, 3 times 3 minus 6, that gives you, whoops, it gives you 3 vibrational modes. Ethanol, what is that, CH3CH2OH. Oh goodness, 1, 2, 3, 4, 5, 6, 7, 8, 9. Good God, I don't even know what that is. Pause. Go team, 21. So you've got 21 vibrational modes. And then you've got, right, so a lot of vibrational modes that can occur there. And if you think about what this looks like, so I'm used to trying all of the molecules out this way for my Chem Art class. Go team. Okay, so think about what all of these look like. So you've got this bending, you've got this stretching, you've got this stretching, stretches, but then you can also have wagging, you could have scissoring, you could have, this one's fun. So when you've got 3, you can get like asymmetric this way, and you can get symmetric this way, but then you can get asymmetric where one of them's going. So it's like 2 of them are in symmetry, or so 2 of them are symmetric and one of them is asymmetric. There's a lot of fun stuff you can do with inorganic salts with that mode. So lots of complications. Okay, with CO2, you can have, so you've got the symmetric, asymmetric, and then you can have bending. Okay, so let me jump back over to the spectra so you can see that. All right, so there's our OH bend and OH stretch for water, but then look over here, CO2. So the stretching, okay, well, we'll keep doing this for a second. So the stretching has 2 bands underneath it, and then the OH bend is actually quite broad. It is a really low wave number. So, because it takes quite a bit of energy, or it doesn't vibrate at a very high frequency at all due to its double bonds. But then you get down to ethanol. Look at all of this craziness. So you've got multiple types of vibrations, some of which involve 2 atoms and some which involve 3. So the CH bends. So that's going to be about 2200 or so. The CC stretch, much lower. Go team. And then the OH stretch, kind of dominant by itself over here. The CH stretch, also a really high frequency. Nowhere near as high as OH, but you've got it's basically due to the fact that you've got electronegativity. Oxygen's going to pull the electrons a little bit farther or closer to it, so that your hydrogen's going to be less bound, so it's going to vibrate at a little higher frequency. The CC stretch is going to be much lower. Think about the difference in the mass between CH and CC. Okay, cool. So one of the things that we do as spectroscopists is we do band assignments to where we're looking at how do you interpret what these larger bands are going to be. So I want to bring you to this plot. Yeah. So this is water. And so here's the bending mode, 1640-ish. Mine was a little lower. And so here I want you to see the symmetric versus the asymmetric stretching. So notice how there are 2 peaks, this green one right here and this red one right here, overlapping slightly. So this is called a deconvoluted spectra, where you've done what is called curve fitting. So you fit multiple curves underneath the big one. So this is the experiment, or the experimental data that you would get from the interferometer. These are the little bands that you would add in to determine, okay, well, what makes up this bigger band? So if you have insight into how many vibrational modes a certain molecule will have, you can then use different models to determine, well, is it dominant symmetric stretching? Is it dominant asymmetric stretching? Which one's going to have a higher population of states occupied? And it turns out with water, symmetric stretching is much more favored, which is why the asymmetric stretching creates, this is what we would call a shoulder. And so when you're doing curve fitting, you might see that this one's actually a little bit more skewed out. And if I go back to the infrared here, yeah, you can really see it. And this one, the asymmetric is much more preferred. So depending on the, and this is beyond an obvious shoulder. So here's, you have a definite shoulder. So there's a dominant peak is right there. There's going to be another one hidden around right there. And so part of spectroscopy is going to be identifying from bands that are all combined somehow, and to see which ones, or if you can separate them out into their unique vibrational modes. It's a lot more complicated. And it becomes, and so just ethanol, which is a very simple molecule, becomes quite cumbersome. Now, if you have mixtures, then if you have liquid phase, gas phase, so gas phase CO is going to be nice and easy. Liquid phase, much harder, because then you've got coupling between the vibrational modes of this OH stretch might couple with other OH stretches, i.e. a hydrogen bond, and broaden this peak. And that's when a lot of deconvolution would be done to isolate which particular peaks go with which types of hydrogen bonding. Okay, go team. I hope that's fun. I hope that what you're doing in terms of spectroscopic transitions with the HCl DCl problem, it has direct application into any IR you could want to do. So you can do the exact same stuff with this, but of course you wouldn't have to take into rotational modes, because the rotational modes are so close together that you can't see them. They're not separated out. They're all underneath those fundamental transitions. Or you've got liquid phase, and then they're blended together anyway. Go team. Okay, email with that questions. The next video, I'm going to talk about IR versus Raman. Raman, I'm excited. Bye.